Assalamu alaikum, my dear students of Pharmaceutical Analytical Chemistry 1. Today we will have a new lab, practical number 7, for the quantitative determination of very weak acids. The very weak acid sample we have today is ammonium chloride. As we agreed that the reactivity of ammonium chloride with bases, it's very slow, so we cannot do direct titration for that, and that's why our experiment today will involve indirect titration. Of course, ammonium chloride and all the chemicals we are going to use today, it's water soluble, so our titration system will be aqueous. And since the ammonium chloride is an acidic or very weak acid, so it can subject to acid-base reaction. That's why we will consider acid-base principles in our titration today. Okay, so let's start as we learned before. Before starting any titration, we have to do the design of the experiment, which is started by usually titrant preparation. Then we have to do standardization of that titrant. Then we have to titrate our analyte. So these are the three major steps. Now let's go to the first step, which is preparation of 100 ml of 0.1 molar sodium hydroxide solution. We agreed that we have to know, first of all, sodium hydroxide is present in the lab in form of solid or liquids. If we are going to look here, we will find out this is sodium hydroxide. It's present in form of pellets, and so the equation we are going to use is as following. Molarity will be equal to the weight subdivided by the molecular weight for each 1000 ml of the solution. Okay, now we know that the molarity required is 0.1 molar, but we don't know what is the weight we have to take, and we know that the molecular weight of sodium hydroxide is 39.997 gram per mole, once again per 1000 milliliter. From that, we will get that the weight needed to prepare 100 ml is equal to 3.9997 grams. But actually we don't want to prepare 1000 ml, we need to prepare only 100 ml, as you can see here in the question. So I will say that the weight needed for 100 ml, it will be, we will subdivide this number by 10, so it will be 0.3997 grams. How we are going to do that? We are going to use the analytical balance to get that weight. Then we will place the pellets inside the volumetric flask, and this volumetric flask of 100 ml capacity, then we will fill up with distilled water slowly. Then we will once again try to dissolve the pellets till completion of the total volume, till the mark of 100 ml. So that's how we are going to prepare sodium hydroxide solution. Now let's go one step further to the preparation of hydrochloric acid. First question we have to ask ourselves is, hydrochloric acid present in the lab in the form of liquid or solid? Stock 1. If we are going to look here, we'll find that hydrochloric acid present in the form of liquid, and the concentration of that is 37%. So we're going to use the other equation, which is molarity number 1 multiplied by volume of the first solution will be equal to molarity of the prepared solution multiplied by the volume of the prepared solution. Or we can say C1V1 equals C2V2, but since here we have the molarity is in molarity, so I will write, instead of concentration, I will write molarity. So the molarity of the prepared solution we want to prepare is 0.1, so this one will be 0.1, and we want to prepare 100 ml from that solution. Okay, so now we have to write the molarity of the stock solution. As you noticed that the concentration of our solution it is 37%. We have to convert it from percentage form into molar form, which is equal to 10.1 molar, as we already discussed that in the previous lab. So I will write it here immediately, 10.1. Then the only unknown is V1. So V1, which is the volume I have to take from the stock solution, it will be equal to 0.1 multiplied by 100 and subdivided by 10.1. So let's get that by the calculator. So it is 0.99 milliliter. How we are going to do that? Once again, we will get our volumetric flask with total capacity of 100 ml. Then we are going to put here the 0.99 ml of HCl. Then we are going to dilute it using the distilled water. Of course, if we have huge amount of HCl, we cannot add water to acid. But in this case, if you notice, we have only 1 ml of HCl. So in that case, it's safe if we are going to add water to acid. But the usual procedure and the standard procedure, which we have to follow, is addition of acid to the water, not to the reverse. So we are going to fill up with water till the mark of the 100 ml. After that, we are going to proceed with the titrant standardization. How we are going to do that? It's very simple. We said we have certain steps we have to follow. We here have two titrants we prepared. We prepared sodium hydroxide solution and we prepared hydrochloric acid solution. So we have to standardize each of them individually. So I will start by standardization of sodium hydroxide. How we are going to do that? We have to standardize it using potassium hydrogen phthalate. This is the potassium hydrogen phthalate. So I'm going to use it to titrate the prepared sodium hydroxide solution, and I'll find out the outcome, which is simple acid-base reaction. So for sure I will have a salt, and this salt I will call it sodium potassium potassium phthalate, because here I call it potassium hydrogen phthalate because it contains potassium and hydrogen, while here it contains potassium and sodium. So I will call it sodium potassium phthalate in addition to water. From that equation, we will get the stoichiometric factor. So here we have 1 mole of sodium hydroxide will be reacting with 1 mole of potassium hydrogen phthalate. So the stoichiometric factor here is 1 to 1. Let's start by the titration component. The titrant in this reaction, it will be potassium hydrogen phthalate, and we will take from that 0.20422 grams. The analyte is sodium hydroxide solution we just prepared, and the indicator we are going to use here is phenolphthalein indicator, and we will use 5 drops. Again, the number of drops of phenolphthalein will be dependent on the concentration of phenolphthalein I prepared. Usually we use the standard way to prepare phenolphthalein, but if it is diluted, so we will need more amount of the phenolphthalein. Specific condition, we don't have any specific condition needed to complete this reaction. So next, I will do to the titration layout. I know in the purette, I will put sodium hydroxide. And here in the conical flask, I will put 0.2042 grams of potassium hydrogen phthalate. But this amount is in powder form, so I have to make it soluble. So I will add to that up to 10 ml of distilled water, just to dissolve potassium hydrogen phthalate, so it will be liquid-liquid titration. In addition to that, I put an indicator, which is 5 drops of phenolphthalein. And then I will write the finding according to the experiment and the titration outcomes, and then I'm going to get the molarity of the sodium hydroxide. Let's go to the next step, which is the standardization of hydrochloric acid solution. So how I'm going to standardize the hydrochloric acid solution? It's very simple. I will use sodium carbonate. So to standardize HCl solution, we will use sodium carbonate, and this is totally different from the sodium bicarbonate. So I will write it here, the reaction HCl plus Na2CO3 will result in, this is acid-base reaction, so for sure I will have a salt, which is sodium chloride plus water, and this reaction will show the liberation of carbon dioxide. Okay, so let's balance this equation. I have here two atoms of sodium, and here I have only one, so I have to multiply this part by 2. Now I have 2 atoms of chlor, so I have to multiply this one. So now the balance is balanced, and the stoichiometric factor between the titrant and the analyte is 1 to 2. Okay, so now let's go to the titrant. The titrant of this part of the experiment is sodium carbonate, and sodium carbonate we will take from it 0.053 grams. While the analyte is HCl solution, the solution I just prepared, and I would like to standardize it. And the indicator for that part of the experiment, it would be methyl orange. Okay, so I will take 5 drops of the methyl orange. There is no specific condition, however, in some other experiments you may notice that the formation of carbon dioxide, we need to heat the solution to expel it, but no need in this experiment. Okay, let's go to the titration system layout. In the purette, I will place the HCl solution I just prepared and I would like to standardize it. And in the conical flask, I will put sodium carbonate, (0.053 grams, and again I'm going to dissolve that using 10 ml of distilled water, and I will add to that, as we agreed, 5 drops of methyl orange, and then I will proceed with the titration and I will get the result and I will continue the calculation. Next, I'm going to do analyte titration. How I'm going to do that? We said this is indirect titration, as we explained in the theoretical part of that practical. So we are going to proceed by adding 20 ml of sodium hydroxide to 10 ml of ammonium chloride. We are going to do that in conical flask. So the reaction will be as following. So this is sodium hydroxide plus ammonium chloride. It will result in sodium chloride plus water, because this is simple acid-base reaction, in addition to liberation of ammonia in form of gas. That's why during the experiment we will notice that there is smell of ammonia. However, we have to do this experiment under the fume cupboard, and we are going to test it using the universal pH indicator, which is a strip. We will put it on the top of the flask. We will see that in the experiment. Let's balance the equation. It is already balanced. So now we are going to boil to evaporate the ammonia, form it, and then we have to take whatever the flask contains and we will start titration with HCl. So the reaction here would be as following: HCl, which is standardized HCl, with the sodium hydroxide, which will remain from this reaction, so I will call it sodium hydroxide remaining. It will result into sodium chloride plus H2O. Very simple reaction, and it is already balanced, so the stoichiometric relationship between them is 1 to 1. The titration component, we will get it from this equation. So the titrant here, it will be HCl solution, the standardized one, while the analyte, it will be sodium hydroxide solution, and I will write between brackets the remaining part. And indicator, for sure it will be phenolphthalein, which is 5 drops. Of course, we explained in earlier labs how we determine the indicator from the titration curves, and there will be no specific condition for that reaction. Okay, so let's move one step forward. After doing the experiment, we will get the results and then we will start the calculation. Calculations will be greatly dependent on the following procedure. We have to subdivide the titration here, which we already done, between the remaining amount of sodium hydroxide and the HCl solution. So we will say the first step of the reaction is reacting between ammonium chloride and sodium hydroxide. Then the second reaction, it would be between the remaining sodium hydroxide and HCl solution, and we are going to start the calculation from this point. So I will just put it in cube and I will call it starting point. So here we will start from this point. We will start the calculation to get the concentration of the ammonium chloride, and we are going to see that in this practical, inshallah. Okay, before we proceed with the experiment, we have to make sure that all the equipment and the chemicals are ready for us. So here we have our volumetric flask of 100 ml capacity, Erlenmeyer flask or the conical flask, the measuring cylinder, small beaker for cleaning purposes, and the glass funnel, in addition to rubber pipette and the serological pipette of a capacity of 10 milliliters. Here we will have our universal stand with the purette, and then we will move to the chemicals required. We need phenolphthalein indicator, methyl orange indicator, water dispenser, sodium carbonate, potassium hydrogenolate, sodium hydroxide, and hydrochloric acid. Of course, when we are going to handle hydrochloric acid, we will handle it in the fume cupboards. In addition to this instrument, we have to use the hot plate with a magnetic stirrer, and here we will have the analytical balance and weighing paper, spatula, once again the label, and the water dispenser. So now we are going to proceed with the practical part, but before that we have to make sure that we have all the personal protection equipment, including the gloves and the goggles. Okay, we have to start first by balancing the analytical balance. So we have to adjust it here by this knob and make sure that the bubble will be in the middle of the circle, red circle. So yes, now it is leveled. And we have to make sure that all the surfaces of the analytical balance it's clean, so we can take out any remaining dusts. If it is necessary, we can remove the component of the analytical balance, clean it and return it back, but it's already clean. So now we are ready to use the analytical balance. Okay, we will have the weighing paper. We will press on 0 or tear and make sure that there is no shakings or agitation around this balance, so we will get an accurate measure. As I said before, it's not that very much important to get the accurate weight of sodium hydroxide, because as we can see here, it is already pellets. So these pellets, it would be difficult to get the exact amount we want, which is as per what we calculated, 0.399. So we will get as close as possible to that reading. So now we will start adding sodium hydroxide. We make sure that we cover the bottle so it will not absorb any further moisture. You will notice that, yeah, now it will be stable once we have seen this arrow, so it is ready to be used. Yes, there is a little drifting in that balance, but it is okay. So now the reading is 0.38 and I want 0.39. I think this is the maximum amount. If I added one extra pellet, it will massively change the reading of the balance. So this is just enough for now. Okay, now we are going to take this amount of the sodium hydroxide and we will place it inside the volumetric flask. Then we will add distilled water. We'll add few amount of distilled water to make sure that we can dissolve sodium hydroxide properly. Then we will continue to add sodium hydroxide till the entire amount is soluble. Of course, we may use heating, but this would change the volume of the water, so the measure of the content of the volumetric flask would not be that accurate. So we will go slowly till we dissolve the entire quantity of the sodium hydroxide. Now we can close it using the glass stopper and gently swirl it. Now we can add additional amount of distilled water. Once again, we'll close it. Then we will complete the volume till the mark of 100, so we have to keep it on the level of our eyes so we can check the meniscus. It's better to put it on flat surface. So now I got the exact amount with the lower meniscus adjusted with the mark on the volumetric flask. Now you will notice that the entire amount of sodium hydroxide pellets are totally dissolved, and we are ready for the next step of the experiment. But before proceeding, for sure, we have to write or make a label for that, so we will not get confused with other solution in the lab. So we will call this one as sodium hydroxide solution. And now it is ready. We will now proceed with the second stage, which is preparation of HCl, so please stay with me. Now we are going to proceed with the preparation of HCl solution inside the fume cupboard. So first of all, we have to run the suction and the light, both of them. Then we have to place our hand here to make sure that there is suction force, so whatever the toxic fume inside the fume cupboard, it's already sucked out. Then we can proceed. We will keep it open till this range so we can protect our face in case of any harmful event happened, and we will proceed right now. We are ready to prepare HCl solution. As we said, HCl solution, we handle it only inside the fume cupboards, because as you can notice here, once we open the cap of the HCl solution, there will be fumes coming out, which is toxic fumes. So we shouldn't do that in the open space of the lab. We have to do it only in the fume cupboard. So we had a few amount of HCl and we place it here inside this container, so we will avoid spoiling the entire amount of hydrochloric acid, because even if we cleaned the pipette so many times, we are not sure if it would be that clean or not. So now we are going to use this volumetric pipette. So we are going to proceed now by taking 0.99 ml, which is about 1 ml from the conical flask. Once again, we have to put it in our eye level, so we will make sure that it's precise reading. I'm not sure if you can see me or not. Okay, so now I had that amount, then I will place it inside the volumetric flask. Take care, this pipette, it's not serological, it is Morse pipette, so we have to make sure that the extra amount will be returned back to the stock solution. Now we will add distilled water. As we said, the amount of HCl added is not that much, so it's okay if in this case we are going to add water to acid. Then we are going to gently mix it. I'm sensing the flask, it's totally at room temperature, so it is not overheated, as what will happen if we are going to use huge amount of conc acids. So now I have to just fill it, and I have to put it on flat surface, and I put my eye on that level, so I will adjust the meniscus properly. I think mission accomplished. Now we are done. Once again, we are going to mix it properly. Then I'm going to write a label, and I will call it HCl solution. So now my HCl solution is ready. and I proceed to the next step. Now we are going to proceed with the standardization of sodium hydroxide solution. So we have to take 0.2042 grams of potassium hydrogen phthalate. So we will have our weighing paper. I usually prefer to tilt it so it will not spoil the content inside the balance. So now we have to take the exact amount. I think this is the closest reading I can get it. So as we agreed before, we have to record all the readings once we got it. So we will call it trial 1. The weight is 0.20. Just wait for the balance to be stable. Now we got the mark. So it's 2030. So this is the first trial. After that, we will proceed with the titration or the standardization of the sodium hydroxide solution, and we will say that the start point is and the end point is. Then for trial 2, we will see whatever the weight, then the end point. So this is trial 1, this is trial 2, and this is trial number 3. So this all for the standardization of sodium hydroxide. Now we are going to transfer that amount. We know that that balance have minimum drifting, but it's okay within the acceptable range, because we already done calibration, if you remember that. In the first lab we had it this semester. Now I'm going to make sure that all the amount of potassium hydrogen phthalate are transferred to my conical flask. Then I will proceed with the titration. After having the exact amount of potassium hydrogen phthalate, which is 0.203 grams, we are going to start standardization of the prepared sodium hydroxide solution. As we agreed before, first thing we have to do is to make sure that the purette is closed. Then we will use the washing beaker, and then we will wash the purette with distilled water. Of course, this to make sure that the purette is totally clean and not containing any remnant from the previous experiment. Next step, we are going to use the funnel. Then we will add sodium hydroxide, few amount, just to wash the purette. We do this step to make sure that the purette does not contain any chemical which may be reactive with sodium hydroxide and may result in negative titration error in the final reading. After that, we will close the valve again, and then we will fill the purette using the prepared sodium hydroxide solution. We have to do it very carefully to make sure that the purette is not overloaded, and we have to make sure as well that the funnel does not contain huge amount of solution, so we will use the control later on. Now, first step, I have to make sure that this lower part of the purette after the valve is filled with the solution. So now it is filled. Now I'm going to remove the funnel and I'm going to adjust the meniscus, but I have to make my eyes on the same level of the zero. Yeah, now the lower meniscus of the solution is on the same level of the zero, so now we are ready to start titration. Before proceeding, we have to put a piece of white paper here so we can notice clearly any color change. Now we will take our potassium hydrogen solution and we will add to that 5 drops of phenolphthalein indicator. I'm not sure if you can see it or not. Let me just check the camera. Yeah, I think it's clear for you now. Now we are going to proceed with titration. As I told you before, we have 2 scenarios. We can do quick titration, and we already have done that, and we found the approximate volume, which is around 10. So now we are going to proceed with the slow titration by going rapidly to 7 milliliter. Then I will start slowing down. Now it's 7 milliliter of sodium hydroxide. Now I'm starting to go slow down drop by drop, so I will get the accurate endpoint. For sure, I have to make sure that I'm doing continuous shaking till the color change. Now I can see that the color takes longer time to be dissolved, to disappear. So now I have to go very slowly to avoid over titration and exceeding the endpoints. Okay, one more drop. Yeah. So now we have reached to the endpoint, which is 10.4. So this is the start point of the first trial. It was 0 and the end point is 10.4. Now we are going to repeat the experiment by weighing again 0.2042 grams of potassium hydrogen phthalate or any equivalent amount. Then we will proceed with the titration, and we will do this trials up to 3 times, so we can fill up the 3 trials. So after doing the experiment, which is the standardization of sodium hydroxide using potassium hydrogen phthalates, I got the following reading. The first way I got it was 0.203 grams, and the end point was between 0 to 10.4, so the end point is 10.4. Same for the second trial and for the third trial. Now I'm going to transfer all this data into the worksheet so I can proceed. So here, the flask content, it would be 0203, 02046, 02034, from 0 to 10.4, and here from 10.4 to 20.9, and here from 20.9 to 31.3. So now I'm going to get the volume consumed. For the first one, it's 10.4. For the second one, it's 10.5. That's very good. 31.3 minus 20.9, so it is again 10.4. If you notice that all our results are very close to each other, it means our work is precise. So now we are going to get to the average of this. So it is 10.433 milliliter, which is the end point or the average of the volume consumed. Now we are going to get to the average of the weight. Okay, 0.2046 plus 0.2034. So it is 0.2037 grams. Okay, as I told you in the earlier labs and the aerial labs we had it before, I just want to make sure that the battery is working, so hold on please, I will put the charger. Okay, now we will proceed. I'm sorry for that. Okay, now after having all these records, we will start doing the calculation, but as I told you before, you have to train yourself too many times about the practice of the calculation. Here I will do the average only, but remember that in your worksheet when you submit it to me, you have to do the calculation 3 times for each trial individually. Okay, the equation I'm going to use here, it would be molarity of analyte multiplied by the volume of analyte will be equal to the weight of titrant, and this one is in milligrams, subdivided by the molecular weight of titrant multiplied by stoichiometric factor, which is number of mole of analyte subdivided by the number of mole of titrant. So the unknown in this step of the reaction, which is the molarity of analyte, we are going to multiply it by the volume, which is the end point. Okay, so let's go back to the calculations. Okay, so this is the molarity of analyte multiplied by the volume of analyte consumed here, which is 10.433, will be equal to the weight of titrant. Weight of titrant, we will get it from here, which is 0.2037, and we agreed that this weight is in grams, but we have to convert it into milligram. So simply I will multiply it by 1000. Then I'm going to subdivide this reading by the molecular weight of the titrant, and we agreed that the titrant is potassium hydrogen and the molecular weight of that is 204.22. So then I will multiply it by stoichiometric factor, which is number of mole of analyte, which is 1, subdivided by number of mole of titrant, which is 1, so it will be multiplied by 1 by 1. So molarity of analyte will equal, let's calculate it, 37 multiplied by 1000 subdivided by 204.22 subdivided by 10.433. So it is equal to 0.0956 molar. So this is the molarity of the prepared sodium hydroxide solution. If you can notice that we already want to prepare 0.1, but we got 0.0956. If you remember, this is due to the inability to take this exact amount. So we took, I think, 0.34. So we had lesser amount, that's why we will have lesser molarity. But anyway, we are sure that the solution inside the volumetric flask now, the molarity of that is 956 molar. Let's proceed with the second part of the experiment. Okay, now we are going to proceed with the standardization of HCl solution. And as you know that to standardize HCl solution, we need sodium carbonate. So as we know, sodium carbonate, it may have hygroscopic property, but we are already using sodium carbonate, which is anhydrous. But we have to make sure that all the moisture contents in the sodium carbonate was removed. So we will do something. We will take few amounts of sodium carbonate on a watch glass, and we are going to heat it in the oven. So we will make sure that all the content or all the moisture content in the sodium carbonate is removed. So now we are going to place our sodium carbonate inside the oven. We adjust the temperature at 110 degrees Celsius, and we will keep it for 5 minutes. So let's proceed. Now we have sodium carbonate after being heated in the oven. Now we're going to take from that amount the exact contents we needed to standardize the HCl solution, the prepared HCl solution. and this is our conical flask. So from this amount we're going to take 0.053 grams. So first of all we have to make sure that it's stable. 0, now it's stable. As I told you, we have a little drifting in that balance, but it's okay. Now we have to wait for the balance to be stable. Now it is stable, so here we will do the trial 1 and we will say the weight is 0.0536. Keeps moving, so I know we have drift, so let's wait. So 538 grams. Now we are going to transfer this amount to the inside of the conical flask. Of course, we have to add distilled water to make sure that all the amount was transferred successfully. After that, we will proceed with the titration, and we will say this is the starting point and this is the end point of the first trial. And then we have to proceed with trial 2, start point and end point. Then we have to proceed with trial 3, starting point and end point. And that's all for the HCl standardization. Now we are going to proceed with the titration. Now we are going to proceed with the following part of the experiment, which is standardization of the prepared HCl solution using sodium carbonate. This is the amount of sodium carbonate we got from the balance, and we dissolve it in few amount of water, then of distilled water for sure. So now we are going to proceed with the titration of the HCl, and we are going to use the methyl orange as an indicator. So I'm going to take 5 drops of methyl orange. 1, 2, 3, 4, 5. If you notice that the color now it is orange, so the end point will be once the solution turns into red. So let's proceed. So the color changed right now. So now we are going to get the measure. We already started from the point of 19. So now we are at 27.7. And this is our first trial. Now we are going to proceed with the second trial. So these are the results after the 3 trials. Now we are going to proceed with the calculations. So now we are going to transfer these records into the worksheet. I already started by transferring them, so please follow up with me. Okay, this third trial was 0.054, and here it was 27.7 and up to 35.7, and here it was 35.7 up to 7. Let's just calculate the difference between them. So we can get the end point, 27.7 minus 19, so it is 8.7, and then 35.7 minus 27.7, so it is 8, and 44.7 minus 35.7, so it is 9. So let's take the average of that, so 8 plus 9 plus 8.7, so divide by 3, so the average is 8.567 milliliter. This is the average endpoint. Let's calculate the average of the sodium carbonate used. 531 plus 0.054, so divide by 3. Yeah, I think this is a logical result, so 0.0536 grams. Once again, I'm telling you that when you submit your worksheet, you have to make sure that you have done the calculation 3 different times, but for me here, just to save time, I will consider the average. Okay, so once again, the method of calculation here will be dependent on the following equation. Molarity of analyte, volume of analyte will be equal to the weight of titrant subdivided by the molecular weight of titrant multiplied by stoichiometric factor, which is number of mole of analyte subdivided by the number of mole of titrant. Now we are going to continue the calculation. The unknown here is the molarity, so this is the unknown, multiplied by the volume of analyte, which is 8.567, equals to weight of titrant, which is 0.0536, but again this weight is in gram, so we have to multiply it by 1000, so I will get it in milligram. Then I will subdivide it by the molecular weight of the sodium bicarbonate, and I'm going just to calculate it. Okay, it's 105.99 multiplied by the stoichiometric factor, which is number of mole of analyte, where the analyte, this is analyte HCl, subdivided by the number of mole of titrant, which is 1. So now we are going to calculate the molarity of the prepared HCl solution. Okay, so it's 0.0536 multiplied by 1000 multiplied by 2. Okay, subdivided by 105.99, subdivided by 8.567. So this is the molarity, 0.118 molar. So this is the molarity of the prepared HCl solution. We are going to use this molarity in the later calculation of the titration of the remaining sodium hydroxide. Okay, now we are going to move to the next step, which is mixing up 20 ml of sodium hydroxide solution with 10 ml of ammonium chloride solution in a conical flask. So this is sodium hydroxide solution. I will use more pipettes to take 10 ml, then I will take another 10 ml later on. Okay, this is the first 10 ml. Now I'm going to take the second 10 ml of sodium hydroxide solution. I have to radiate the bubble first, so it will suck more quickly. Now the meniscus is well adjusted. So now I'm transferring the second 10 ml to the conical flask. Okay, so now I will return the remaining amount to the sodium hydroxide volumetric flask. Now I'm going to add the sample solution, which is ammonium chloride. I have to take 10 ml, so this time I'm using serological pipette with total volume of 10 milliliters. chlorides. Now I'm going to shake them well, and then I place them on the hot plate. What's going on right now? Actually, the reaction between sodium hydroxide and ammonium chloride is taking place, and it will result in liberation of ammonia. And as you know, ammonia is a basic chemical. So how we are going to test that? By using the universal indicator strip. I will simply place it here, and I will find out what will be the color change. The color change should be similar to the pH of ammonia, which is around 10 to 12 or 10 to 1150. So I'm expecting this scheme of color. So we have just to wait a couple of minutes till the reaction starts and ammonia start to go up. I'm adjusting the temperature to be around 70%, so I think it will take a few minutes. Now, if you can notice, there's few amount of the fumes that are coming outside, and I'm sure that the fume cupboard is protecting us from smelling such harmful gases. However, you still can smell very low concentrations of ammonia, which is very common odor, and you can easily recognize it. Okay, if you can see now the color change here, the scheme, just compare it here and you'll find out what is the color. So once again, we will go back here and we will immediately try to compare the color. So I'm telling you, the gas liberated now, it is ammonia. So if you're going to compare it, yes, it is ammonia. So we will continue boiling till no further ammonia will be liberated outside the conical flask. So I'll just pause the recording just to save your time. Okay, after a while of boiling, now we are going to test if ammonia is still yielding from that reaction or not. So simply I'll put another universal indicator strip, and I'll find out if the pH is basic or neutral. Okay, as you can see now, the color scheme of that is identical to the neutral pH. It means there is no further ammonia is getting outside from that reaction. So I will consider the reaction is completed, and now I'm ready for the second step of titration. So let's go and do that. So now we will proceed to the last part of the experiment, which is titration of the remaining amount of sodium hydroxide that remained inside the conical flask after being heated with ammonium chloride. So to do that, we are going to fill the burette with HCl solution. Then we are going to adjust the meniscus of the burette, of the solution inside the burette, to the mark 0. Yes, now the lower meniscus is well adjusted. And we will add 2 drops of phenolphthalein. So notice that the solution turns pink because the media inside now it is basic due to the presence of the remaining amount of sodium hydroxide, and now we are going to start titration of that amount. Of course, in this time we will not do the rapid titration and slow titration method because we already boiled the sodium hydroxide with ammonium chloride, and it will take a lot of time to reboil again. So we will just go slowly, drop by drop, from the beginning. Okay, let's start. Notice that the color starts to faint out. Now it is clear. I think I need one more drop. Yeah, now the solution is totally clear. It means I already reached to the end point. So the first trial was 7.1. So here I have to write again. This is trial number 1. Okay, so in that trial we have the start point of 0 and the end point was 7.1 milliliter. So we have to repeat this experiment at least 3 times. So we will get the average of that reading in each time. Okay, now we are done with the titration of the remaining amount of sodium hydroxide using HCl solution, and these are the readings. So I'm going just to write it here. So the flask amount in each time, it was 10 ml, or supposed to be 10 ml. Start point 0 for the first trial, and the end point of the first trial, it was 7.1. So the volume consumed is 7.1. For the second trial, from 7.1 to 14.3. And then for the third trial, it was from 14.3 till 21.2. So let's just calculate the difference between the readings of the second and the third trial. Minus 7.1 equal 7.2. That's good, so very close to the previous result. And then 21.2 minus 14.3. So it is 6.9. Again, it is close. So let's calculate the average. Subdivide by 3. So it is 7.07. Okay, or 67 milliliters. Okay, so these are the readings. So now we are going to calculate it, and it's very simple calculation, by the way. Let's start from this point. If you remember, I told you in the beginning of the lab that this point would be the starting point for the calculation. We know that the molarity of HCl we prepared, we have to go back here where it is. Yes, this is HCl. Where is the molarity? Yes, 0.0118. So the molarity, it would be 0.118 molar. It means 0.118 mole in 1000 ml. But actually of HCl we consumed only 7.067. So we will calculate number of moles in 7.067 ml, which is equal to, just cross multiplication, very easy calculation. 67 multiplied by 0.118, subdivided by 1000. So this is the number of moles of HCl, 0.00083 moles. We said that the stoichiometric relationship between HCl and sodium hydroxide, it is 1:1. So whatever the number of moles of HCl, it will be equal to the number of moles of sodium hydroxide. So here we know that the number of moles will be equal to 0.00083 moles. Now this is the amount or the number of moles of the sodium hydroxide remaining. Okay, so how we can get the amount of sodium hydroxide that reacted in the first reaction? Simply we have to calculate something, we call it total moles of sodium hydroxide. It's very simple. We will say that the sodium hydroxide molarity is, let's go back and find out. Yeah, it was 0.0956956. Okay, so 0.0956 moles in 1000 ml, because this is the definition of the molarity. Okay, but we don't have, we didn't consume 1000 ml of sodium hydroxide. We consumed only 20 ml. If you remember here, this is the amount of sodium hydroxide we used, 20 ml. So it's very easy, and the calculation now is straightforward. So how we can get this number of moles? By cross multiplication. We multiply 20 by 0.0956 equals subdivided by 1000. So this is the total number of moles of sodium hydroxide, which is equal to 0.001912 moles. Okay, so to get this amount of moles, or the number of mole of the sodium hydroxide reacted in the first reaction, simply we will subtract this amount from this amount. So we will say 0.001912 minus 0. I think 000, right? 83. Okay, so it would be 0.00108 moles. Okay, and we said that the stoichiometric relationship between sodium hydroxide and ammonium chloride, it is 1:1. If you can remember from this equation, it's 1:1. So let's go back here and let's calculate it. So simply the amount of moles, or number of mole of ammonium chloride, will be equal to the number of mole of sodium hydroxide, which is 0.001082 moles. Of course there is 2 here. Okay, from that number of moles we have to calculate the percentage concentration. How we are going to calculate this percentage concentration? Simply we will do that as following. We will say that for the ammonium chloride, the molecular weight equals to 53.49. Let me get the bottle of ammonium chloride just to make sure that this is the right molecular weight. Okay, let's see it here. Yes, it is 53.49. So this is the molecular weight of ammonium chloride. Of course, we can Google it, or we can calculate it from the periodic table. Okay, so we are saying that in 1 mole of ammonium chloride, it will contain 53.49 gram. But we don't have 1 mole of ammonium chloride. We have only 0.001082. So we will say how many grams are in 0.00108 moles. In cross multiplication we will get the results immediately. So we will multiply by 53.49, so it is 0.057 grams. Okay, this amount is based on our titration, and we say that the amount of ammonium chloride we consumed in the beginning, it was 10 ml. So this amount are present in only 10 ml of the ammonium chloride solution. So how we can calculate the percentage? We know the percentage, it means the number of grams in 100 ml. So this is number of grams in 10 ml. So what would be the number of grams in 100 ml? Cross multiplication, so the percentage concentration, it would be 0.57%. So this is the percentage concentration of ammonium chloride.